It look like a Santa.
Whoa.
Canyon Santa.
That Santa. Is this a silent? And I have to know.
What
It's
sign are
nothing
happening?
red I'm wearing and
Enlighten me. Does Santa still look like what we think of Santa in Kenya? You don't have Santa.
Let me tell you.
You don't have Santa.
Okay,
That's heartbreaking.
wait.
Okay.
Our families don't believe in giving gifts for Christmas.
Really?
Because
This is culture shock to me. Go on. What do you do at Christmas then?
we just come together as family.
Ah, big meal.
Yeah.
Ah.
You know, slaughter goats and things like that.
Okay.
But there's no, if your family didn't get gifts for Christmas, that's a large.
Interesting.
Most people think it's a Western tradition.
Yes, okay.
Yeah.
So just a big family meal. Okay. Does anybody here get gifts for Christmas time?
I want
And I'm sure everybody wants gifts for Christmas, but does anyone actually do this for Christmas?
Yes.
Probably not in China. What's the deal in South Korea?
For kids, celebrate.
Kids get gifts at Christmas? China? You get
No.
gifts at Chinese New Year? Spring Festival, yeah, okay.
Yeah.
Malaysia? What's the story?
No, we don't celebrate.
Oh, Christmas, yeah.
Malaysia, it's Christmas all the time.
We never celebrate.
I'm sure you didn't listen to me picking one.
Is it jelly? Oh, this is jelly gum.
Wow.
What did you think I meant when I said jellies?
Jelly, you know.
Oh, come on! I've got to come back with it.
Yeah, we not. Why people?
Oh yeah, I'll just whip that up in the staff room. Just no problem.
More.
You ate those quick.
Yeah.
You ate those quick.
Okay.
Are you hungry?
Okay.
They're my favourite.
No.
Bruce!
We can go back there.
No jellies?
I was wondering, Monica, come back.
Part of people want
We will leak everything.
KJ, they're all clean. I coughed on it just a little bit.
Let me tell you, Chinese people.
You know, when I was walking back, I had a sneeze and the lid was open and awkward. Just avoid the green ones,
like
okay?
religion, I mean, religious, like, or...
Why?
Because I have heard that China government wanted
Students cannot go to school before 18 years old.
Why?
Because they are children. Government don't allow the children to go to the church.
Because many missionaries go to China, but it's really hard to have life to go to.
This is our last class before the exam? Do you have more classes today? Wait, you came in just for this class? I feel so honoured.
Yeah, just for you.
I'm touched.
You had to wear clothes and stuff.
So, more jelly.
Oh, so sorry you had to get dressed and come to school. To apologise for that.
What is this?
I think that's like a baby suitor, you know, the babies they put in their mouth,
Oh, actually.
or that, could be a ring. It doesn't matter, you eat it anyways. Ah, KJ.
I'm doing Santa.
Okay, Ben, I really don't know what to do on Christmas.
Eat.
Eat.
Okay, Monica, you can sit down now.
Also on Christmas.
We can just pass it around if people want more.
No, just keep it.
Okay, Jay. Oh. I wonder what I did in a past life to be punished by teaching this class. I must have done something terrible. I must have killed people in a past life. This is my punishment now.
No, you with me.
Huh?
You with me.
That's also.
Yeah, you group two
Yeah,
people.
double pun. Yeah, must have been serial killer or something. Right, what do we need to see stuff from version 2? What's the story? You only looked at version 1?
Yeah.
Let's just do it.
Yeah, well, you don't need me to do all of it because that would be a waste of time, because some of the questions I'm sure you think are easy. So why don't you find some questions you think you can't do and you need me to do?
Yes, let's do this.
Yes.
Potential divider circuit can be used to provide an input.
Wait, what question is this first? Let me write down.
Okay, B3
B3.
from positive to zero.
Yeah. Okay, potential divider.
Circuit can be used to provide an input for control electronics.
Hang on, input is 400?
For control electronics as a
Wait, it's
example,
what?
As a
No, go back.
No.
Okay, go on.
a light dependent resistor.
Okay, that's all just blah blah blah. Get to the
Yeah.
juicy part.
Has a resistance which decreases as the light level.
Yes.
Draw a circuit diagram for a circuit with a battery as its power source, containing a resistor and an LDR in a potential divider.
Okay, so you know for the potential,
Well, that's version 1.
it might be the same question in version 2.
No, it's not.
Is that version 1 or version 2?
Yes, for the one.
Oh, alright, version 1, fine. So you've got 2 resistors here, okay? You've got one which is fixed and one which changes. For the potential divider, if we think about the formula, V out equals, what is it, R2 over R1 plus R2 V in. I suppose technically either one could be changing. I'll just put this one as R1 and this one as R2, and I'll make this the one that changes. Okay, so how many marks were drawn on the diagram here?
4.
4 marks. Alright, did they tell me how big the battery or the resistors are or anything? No numbers yet? Alright, okay, is this part A? A, okay, B?
A1.
A1, okay. A2 now.
If the resistance of your resistor is increased, but everything else remains the same, data explain what will happen to the voltage.
Okay, fair enough. So V out. If R2 increases, what happens to V out?
Increase.
I think it would increase as well. V out would increase if R2 increases. In fact, if you want to be even more precise, if R2 heads to 0, then V out heads to 0, and if R2 heads to infinity, then V out will head to V in. Yeah. So basically, the R2 is somewhere between 0 and infinity, and then the V out will be somewhere between 0 and V in. Okay, that should give me the full marks for that one. What's next, KJ?
To protect ammeters from damage, they are often found with a diode connected in parallel with them in circuit. Explain how this precaution might protect an ammeter.
Interesting. So what they're saying is, when you look at an ammeter, let me draw it here. So this is our ammeter. What is really happening inside the ammeter, you have 2 things. One, you have a little LED diode. And then 2, you have the thing which measures the current. So, it's like I look inside of the box. Remember when we looked inside of the battery, we imagined it as internal resistance and a pure EMF. When I look inside the ammeter, what they say is that it's actually an ammeter and an LED diode. And they say, what's the reason for this? What's the logic? Well,
no.
huh? Well, let's have a look. Let's say this here is I, and this one here is I1, and this one here is I2, and then this comes back to I.
One.
Now, what do they say about the LED diode? Do they say anything about its resistance? No? Okay. I don't think it has to be an LED diode. I think it just has to be a resistor, really. There's nothing particularly special about it being the LED diode. So let's just imagine what would happen if this has a resistance, I'll call it R2, and this has a resistance, I'll call it R1. Okay, and I want to know what happens to the I1 and the I2. Is the I1 and the I2 the same or different? Different. But what is the same here? The voltage. And what is the voltage here in this part?
V.
V, and here is V, and what is V? That's I1 or 2. And the other one?
I1, I2 R1.
I2 or 1. So you can, sorry, they're the same. So I1 or 2 equals I2 or 1. So I1 over I2 equals R1 over R2. So that means I1 compared to I2 will be in the same ratio as R1 to R2. So, for example, let's imagine this had 99 ohms of resistance, and this here had 1 ohm of resistance. Then this current will be 99 over 100 I, and this current here would be 1 over 100 I, because we just said that they share them in the ratio of the resistance. So for example, let's say this is 100 amps, then on the top would be 99 amps, and on the bottom is 1 amp. So what this ammeter could do, it could actually measure the current, and then just multiply the result by 100 on the screen. You know, because it just turns like this. So it maybe measures 1 amp, but on the paper it says 100 amps, because it knows it'll be 100 times bigger. So you might say, well, what was the point in doing that? Well, this way it protects the ammeter, because there's less current going through it. So it's a way to protect it. Of course, the disadvantage is that you're going to waste energy by making heat. So I think I understand why now it's an LED diode, because if it's an LED diode, the resistance will be very, very small. Let's say like 100 milliohms. This means on the other side, where the ammeter is, this needs to be only like, say, 1 milliohm. Because you only care about R1 over R2, it doesn't actually matter how big they are. All that matters is their ratio. So we're able to have small resistance, so not much heat, and we can have a little current going through the ammeter and just multiply the number by 100, and then we have the actual value. So I think I understand why they said an LED diode rather than just a resistor. How many marks is this, KJ? 3 marks? OMG. Give me the 3 marks. What do they say? You got the marking scheme? Yeah. Got some jellies?
Fish.
Fish?
This is, yeah.
That's a fish?
This is fish.
That's B, right?
This one, KJ, what number is this?
B3.
B3. B3A3.
You mean B3 has A1 to A?
3. What's part 3?
You mean the LED terminal?
Yeah.
B3. B.
B3B? Okay.
Yeah.
B3B.
Protection is from too much current and mirror voltage resistance. As current increases, voltage on the mirror increases as voltage on side. diode in power increases very large current allowed to flow, therefore avoiding the ammeter.
I don't like it. I don't like it at all.
Merry Christmas.
Protection is from too much current. Okay, 1 mark for that. As current increases, voltage on the ammeter increases. Well, duh. That's stupid. I don't know. What? Oh, goodness. Ammeter possesses small resistance. Good. I mentioned that later. As the voltage is in parallel, very large current is allowed to flow, therefore avoiding the ammeter. So I said small resistance, 1 mark. Protection from too much current. That's the other point I was making. And also, for the last mark, very large current is allowed. So I can have a large current, I can have small resistance, and it protects the ammeter because only a small current will go through the ammeter. So the other point which they said is not really a point. It says as current increases, voltage on the ammeter increases. I mean, but that's not answering his question of how does the LED protect the ammeter. That's just a statement of behaviour, fact. It'd be like me saying, how does a window keep the room warm? Well, when the teacher drinks the coffee, he feels better. Like that doesn't answer his original question. How does the LED protect? I'm not sure. I'm sure he meant something else by this, but I'm not sure exactly what. It's not clear. Okay, is there more to this question that you need me to do?
It's a lot.
It's a long question? Okay, what's next then?
Here.
Alright, thank you.
And also here.
No, you can read it to me.
No, it's a lot.
Okay, the next part is EMFs. C. In the real world, batteries contain internal resistance, as we know. We wish to investigate using a simple circuit. Now, do you remember the circuit we need to draw to measure the EMF? So you have your battery, and then you have your internal resistance, and you have your E here. And then what else do you have? You have your
Voltage.
variable resistor, yeah, and also ammeter. Probably should put a switch on it as well. And also your voltmeter. There we go, that's how many marks? 3 marks, not bad, okay. Sketch a graph of what you would expect to see. So in other words, for this experiment, do you remember what the graph is? So what do we put here and here?
V and I.
Yeah, which way around?
I prefer the V on the y-axis.
Yeah, V here, I here, and the graph
Like this.
goes down. And what does this represent?
EMF.
And the slope?
Negative R.
Okay.
What is it?
What the heck is that? Alright. Wait a second. 5 marks? Sketch a graph and explain how you would use it to find the EMF. Dude, focus.
Why I want to give you this?
But first I want to give my answer to C. Right, do it! Focus on the question. Thank you. Right, so I haven't answered enough for this because I've done the graph, but I haven't explained how to use the graph and how to make the graph. So, what we do is we vary or, that's point 1, and then we measure V and I, and then we plot V and I, which I've shown here, and then we calculate the gradient, the slope, and then finally we say the OR is equal to minus the gradient, minus the slope. Draw a circuit, sketch a graph, explain how you would find the, and how we find the EMF. We also need to calculate C, and then the EMF is equal to C. Now this is 5 marks. So my guess is we'll have 1 mark for V and I, 1 mark for the shape, 1 mark for this, 1 mark for this, and maybe 1 mark for saying this.
Everything has mark, and then you say max 5.
Okay, everything has a mark and your max is 5.
Yeah.
Nice. Okay.
See, what
Yeah.
is C?
The intercept on the graph. The y-intercept.
Intercept means C.
Yeah.
C means
Yeah. Okay, now part 3. Cars have a battery of 15 volts EMF. Lee,
Yeah.
do you think you could survive from a height, this height? Are we on 3 stories? No, just wondering. You might survive, but your legs will be broken.
Yeah.
I'll think about it. Don't give me reason to think about it more. Okay. 3. Cars have batteries of 15 volts. Starting a car requires a large power supply to an electric motor. Explain why when you start a car, the headlights and the radio, they go dim or they get less power. So in other words, when you turn the car on at first, you get not much power for everything else. Well, if we imagine the car as a circuit like this, perhaps, you would have one really large resistance here, and this is the starter. And this is to start the car. And once the car has started, you don't need the starter anymore. And then maybe over here you might have in parallel the rest of the car. You know, it could be like the lights, it could be like I'll draw a radio, it could be like your GPS, you know, all this type of stuff. Yeah. So what happens when you turn it on? Well, first, this requires a lot of power, which means if you think about the formula power equals IV, basically it means, you know, a lot of current or a lot of voltage. What happens to these guys if this is taking all the power? Well, let's just call this resistance big R, and we'll call this small r, and small r. If I use Kirchhoff here, I can get... no, I feel like I'm making this more difficult because there's only 2 marks. I'll just make it as 2 points. Yeah, kind of essentially it. At the start, the starter requires a large large current, which means the lights get a small current. So my point I wanted to make was, here, look, let's say this is the light and this is the starter. This will need a big current, so I'll call this I big. And if this is I big, then what's left for up here is I small. Now, if this is 15 volts, because this is in parallel, we know that these are both 15 and 15 volts. What's the power on the top? Power equals IV. So that's I small times V. And what's V? 15. And what's the power here? Power on the bottom. IV. What's the V? 15. And the current? I big. So in other words, by the starter getting all of the current and all of the power, it means there's not much left for the lights. Basically the starter is hogging all the power, and the rest of the car, doesn't get much power. Now, why does this not continue? Why is it that after a few seconds it goes back, the lights come back on? You know, when you turn the car on at first, the lights turn off. Why do they come back on then? Well, it's because the starter only needs to do its job to start the car. Once the car has started, then it's no longer needed, so it turns off.
How?
Well, the purpose of the starter is just to ignite and begin the combustion cycle. Once the combustion cycle has started, the starter no longer has a job.
No, so how?
What do you mean how?
How does the controller give this?
How people like starter?
Oh, how? Well, if I remember it correctly, but it's been a long time since I've seen this, you have your piston and you have your wheel here, and this goes up and down and this turns around. So I think what happens in the beginning is I don't know anymore because starters have gotten quite advanced. But anyways, gas goes in here and it gets lit. What lights the gas? What lights the gas is something called a spark plug. Okay, so you need to have some energy to make a spark, a flash, to cause this to explode and to begin the process. Okay, you might even need some kind of energy just to get this wheels turning at the beginning. I don't know, like you might need some kind of small electric motor just to get this spinning at the beginning, just so it's not stuck and it can start moving. I'm not sure, because you see, cars have become more complicated. For example, like I have the hybrid car, and every time I stop, the engine turns off, which means every time I start, the starter turns on. Because the starter needs so much power, the hybrid car needs a separate battery that has a very, very high capacity to charge the starter. Also, because the spark plugs have to work harder, because they have to, maybe every 5 minutes they have to start the engine again. These spark plugs need to be stronger or they'll wear down. Anyways, the starter is just to get everything moving to begin with. It needs a lot of power, because until the engine is running and the petrol is burning, the starter's doing everything. It's like kicking everything into motion. It's only 2 marks.
Yeah.
So what did they say? Do you want to give it to me?
Large power requires large current.
It's like fireman, isn't it? Large power requires... Oh no, sorry, that's great power requires great responsibility. So, large power requires...
Large
current. 2 marks?
No, as voltage discharge rule. When large current flows, it is lost of the internal resistance of battery. The terminal voltage drops, causing the item to switch off.
I don't quite like it. I got 1 mark for saying the current is big, and then 1 mark for mentioning that this one is small. Okay, what's next?
Oh, I wanted to do this. Two capacitors.
Wait, which question is this?
A12.
A12?
Yes.
Okay. A12.
Two capacitors initially uncharged.
2 what?
Two capacitors.
2 capacitors.
Yes, initially uncharged.
Yeah.
Are connected in the following circuit, like parallel.
Cool.
Here.
Alright, I'll draw the picture, thank you. So you got capacitor, 220, this one was 220 microfarads, 470 microfarads. And here we've got 6 volts. When A is closed, how much charge is on the capacitor? Okay, when A is closed, it means it's like this only.
Yeah.
The B is not in the circuit. How much charge? Okay, what's the formula for charge? Q equals CV equals 220 micro times 6, isn't it? What's that now? 6 times 22. 6 times 2 is 12. Is it up 1320 micro? So that is 1.32 millicoulombs. switch A is then opened and switch B is closed. Aha, I like it. So A is opened and then B is closed. So now you have this circuit like this. Because if this is open, you know, we don't care about it anymore. And I kind of see where this is going. This capacitor then is going to charge up this capacitor here. A charge is about to flow. What is the charge stored on the 220 at this time? So in other words, how much charge? Well, the charge is going to come out and enter this capacitor, but it's not like it will just sit there. So what will happen is this will charge up this capacitor
And then charge again.
until they're equal. Because remember, I know it looks like they're in parallel, but they're not in parallel. They're actually like this. They're in series. And you know when capacitors are in series, the charge here and the charge here must be equal. And that must also equal the total charge. Yeah? Yeah? Now, we have previously the charge is 1.32 millicoulombs. Okay, so you might be tempted to say, okay, so then that means that's 1.32 and that's 1.32. But it's not quite like that because they have to share it. And the question is, how do they share it? So let's see. Let's work out first the total capacitance. That might be helpful. If they're in series, how do the capacitance add? 1 over 220 plus 1 over 470. Can somebody give me the total capacitance here, please? One 149 micro, so 1.49 milli. Yeah? 1.49 milli. This is a bit awkward now because it means that the capacitors can hold more charge than what was available to charge them.
Farad.
Of course. No. Oh, sorry. Thank you. Microfarad. 149 microfarads. Okay, so I actually haven't worked out the charge they could both hold. Let's calculate that. Q equals C V. Now, what's the V?
We don't know.
Yeah, but this was charged up using a 6, which means when it begins discharging, it will at first behave like a 6. So it actually is 6 here. Yeah. Got it? What is it? 7?
Wait.
Oh well, it's 894.
Look at me and I...
You're sitting there with a huge graphing calculator. I can see this huge graphing calculator.
It's expensive.
AA2.
Thank you.
Money power. Money power.
882 microcoulombs. So that's 8.82.
1.9 times 6 is 882.
Why?
Dudes.
Because
Hang on, shh.
894.
How'd you give me the wrong number when you have a calculator?
No.
894 is what I said, and I don't have a calculator. 894. So 8.94 millicoulombs. Okay? Which is a problem because that's how much they can hold, but that's more than what can be provided.
Yeah.
So that's a problem. Do you know, I just don't know. Give me a moment to think.
Or
Give me a moment to think.
It's not milli. It's 10 to the minus 4.
I'm thinking. Leave me.
Even
Yeah, leave me in peace. This is a hard one.
Yes, very hard. But how voltage is it?
No, the voltage. The voltage here is not the same. Wait, that's it. You're a genius. The voltage is not the same. The two voltages here should add up to make 6. So it means that when I use 6 here, I shouldn't have used 6. I should have used a number smaller than 6. Because together they should make 6. So now we have to have the job of finding the voltages. Unless Monica has a better way.
No, that is wrong there.
Okay, what is it then?
8.94 times 10 to the minus 4.
Is this right or wrong here?
Where are you finding?
This 1.32.
Yes, correct.
And this one is smaller than this?
Yeah.
I give up. Give me the marking scheme. No, that's a good point. That's a good point. The good thing is, like I said, I'm writing your exam this week, so.
And how about Wheel of Fire?
Oh, dudes, that is hard. Interesting. Can I have your opinion, please? In this circuit, parallel or series? What do you think?
Parallel.
But, okay, this is just a wire, true? And this is just a wire. So I can move it, right? So imagine I just move it like this. The same circuit. Agreed?
Yeah.
Okay, and what if I move it like this? The same circuit. Agreed?
Yeah.
Series or parallel? Which you just said parallel a moment ago. Which is it?
Because there's B.
Well, one way we can know is if they're in series, the voltages should be different. And if they're in parallel, should be the same. So if you look at this and this, what do you think is happening with the voltages? I think these voltages should be the same. Because remember, if we have a circuit like this, and this has a voltage here, and this will measure a voltage here, this voltage should be the same as this. Are they in series or parallel? Well, they're in series. Or not. No, they're in parallel then. So they're in parallel. So it's not in series. So this is the problem then. This is weird. So circuits like this are parallel?
No.
No, that's...
Serious.
I should tell you what they said in the marking scheme.
This is series.
Yeah, but the man.
I shall need to do further research on this topic. Anyways, I'll just give you the outline of what to do here, and then we'll just close this.
The capacitor. Because you use maybe, but it's the positive of the capacitor connected to the positive
I'm not really listening to you, sorry. We're just trying to get this on. I like this question. I might have to put it into my worksheet. Anyways, I just want to show you very quickly how to solve this. So, you have a capacitor. Do we know the C1? Yes. We have a capacitor here. Do we know the C2?
Mm-hmm.
Yes. They're giving it to us. Okay? Now, do we know the Q1? No. That's what we want. Do we know the Q2? No. That's what we want. What is Q over C? It's V, isn't it? Q equals CV, so V equals Q over C. So would you say the voltage here is the same as here? Yeah, it would be. In fact, it doesn't really matter if they're in series or parallel, because when there's only two of them like this, it has to be the same. But you can use Kirchhoff's law to see this as a loop law. Anyways, Q1 over C1 is V1, but V1 must be the same as V2, so you can make this equation. These are unknowns, and these are knowns. Happy with that, KJ? And then we can also say Q1 plus Q2 must equal the answer that we got earlier, the 1.32. Now this is where we do care if it's in parallel or if it's in series. Because you know for capacitors, if they're in series, then this charge equals this charge, which equals the total charge. But if they're in parallel, this charge and this charge together, they add to make the total charge. So this is where we do care if they're in series or parallel, and apparently this is parallel. So we can make this equation, capacitor as parallel.
I have a question.
Because I'm a nice guy like that.
Yeah.
Are you?
No.
Yeah, okay.
Okay.
The semester 2 is gonna be like time schedule is same as semester 1. The 9 to 5 already.
Haven't a clue. Nobody tells me anything.
Because you were here like 10 years. You were
So,
one.
you think that matters?
Yeah.
Wait until you start work. You'll understand.
Because you're gonna skip the January start student also, right?
You're thinking too logically. Too logical. Too logical.
I just want more rest and some space. Because I cannot go to bed. It's not in Monday,
Sorry, I'm
I
not-
can go to bed.
Are you talking or not? Listening to you actually.
I cannot go to bed. I cannot go to the hospital. I cannot go to anywhere.
What?
Oh. Yes.
Give me a space. I know.